Let's look at complex number conversions just to remind ourselves of what's going on. Really, this is all motivated for us right now because we're dealing with solving sinusoidal steady-state circuit problems, or we are wanting to do sinusoidal steady-state analysis. Why does this then end up with complex number conversions? We start looking at impedances for resistors, inductors, and capacitors. When we do that, we actually see that that corresponds to or yields complex numbers. We also, in our sinusoidal steady state analysis, when we go from the time domain into the frequency domain, we now are wanting to do algebra instead of solving differential equations. Because of that, when we have sources which might be voltage or current, those, because we are in the sinusoidal steady state, those are sinusoids. Those sinusoids we can represent, we can keep omega on the side of our paper. We don't have to worry quite so much about the frequency once we get started, and what we really need to concentrate on are the magnitudes and angles, or the phasor representations of those sinusoids. And that then really also is, again, a complex number. We also have been working with complex power, and because of that, it's convenient or helpful to remember how we manipulate or use complex numbers. In general, I think maybe an easy or a clean way to think about complex numbers is graphically or visually or vectorially. These complex numbers now are two parts to those. They have a real part and an imaginary part, and it's really just a function of keeping track of those two pieces. We have a real part and an imaginary part, which, if you think of that as a vector, then the real part, by convention, is the horizontal part of our vector, and we might just call that the real part. And our vector in general has two directions to it. One, if we decompose it into these orthogonal directions, we have the horizontal part, and then we also have the vertical part, and we'll call that the imaginary part of our complex number. We are now able to sketch that in this complex plane. Here's our real axis. Here is our imaginary axis. What we need to be very comfortable with is if we have a complex number, we could think of it having a real part of length r and an imaginary part of length x. Then the complex number is really just the vector sum of those two orthogonal directions, and we can find what that is in terms of a length by looking at the hypotenuse of this, or the diagonal in this box that we've drawn, with two sides, one side being the real part and the other side being the imaginary part. We now can associate the length of that as, let's say, our magnitude of that vector, or the length of that diagonal, and hopefully we remember that that's the hypotenuse of a right triangle, and this angle, theta sub v, can be determined by these two sides of this rectangle. What we're really saying is that this voltage, which we will represent by a V bar, or this complex number, could have a real part and an imaginary part in orthogonal directions. We go horizontally a distance r, vertically a distance x. We could also represent that as a length of that vector at a particular angle, theta sub v. This is then our rectangular form of the complex number, and this is our polar form of the complex number. And what you want to be able to do is go back and forth with those rather easily. Meaning if you now have been given the complex number in polar form, you'll be given this length of the vector and the angle theta sub v, or you could think of that as saying, oh, I'm really walking horizontally a distance r, and then I have to make a 90-degree turn and walk the vertical distance the length of my imaginary number, and there is your right triangle. Meaning complex numbers are really no harder than being able to play or use right triangles. And with right triangles, you can think of starting with two different values or variables describing that triangle. You could start with the length of the hypotenuse, or the vector length, and the angle theta sub v. That then allows you to compute the real part, r, which is just the hypotenuse times the cosine of theta sub v, and the vertical, or the imaginary part of that complex number is then just the length of that complex number, or the hypotenuse, times the sine of theta sub v. You could also be given that information in terms of its rectangular form, meaning you could be given the real part and the imaginary part and have to determine what the magnitude and angle are. Hopefully you remember the hypotenuse as a squared plus b squared is equal to c squared, or that relationship, which in this case says that the hypotenuse length, or our vector length, is the real part squared plus the imaginary part squared, and the square root of that sum. The angle theta sub v is then just the angle that has a tangent of opposite over adjacent, or it's the inverse tangent of x over r. Real quickly, if we simply think about an example, let's just use some 3, 4, 5 numbers, because those are pretty easy to work with. Suppose that somebody gives you a real part of 4 and an imaginary part of 3 for a complex number. Then what they're saying is they're saying that this complex number is 4 plus j3, since we're assuming we need to know the sign of both pieces. Either the real part is going to the right or to the left, being positive or negative respectively, and the imaginary part is going positive or negative, up or down respectively. If you're given this complex number, think of it as a vector again in this two-dimensional space. You're now moving 4 horizontally, that's the real part. Then you're moving 3 vertically, that's the imaginary part. And we now are left with this 3, 4, 5 triangle. Here's our length of the vector, here's our angle theta sub v, and we know then that the length of that vector is 5, but in this case if we compute it, that's the real part squared plus the imaginary part squared, square rooted. We have 16 plus 9, or the square root of 25, which is 5. And we have theta sub v, which is the inverse tangent of the opposite side over the adjacent side, which is the inverse tangent of 3 over 4. If I've sketched that somewhat accurately, you would see that that was then this 36.87 degrees. Hopefully that will help with your understanding and being able to manipulate complex numbers when we need them.